Welcome to another unique study by Dr. Ken Boa, President of Reflections Ministries and Trinity House Publishers. Today, he looks at the pointers revealing God's amazing creation and points us back to God. Here now to introduce this study is our teacher, Dr. Ken Boa.
We're talking about pointers in the microcosm and in the macrocosm. And when we admire great art such as Leonardo da Vinci's Mona Lisa, we look at it from a variety of perspectives. We consider the emotions that the painting evokes from us, and we try to understand Leonardo's meaning. We scrutinize the ambiguity of Lisa del Giocondo's ineffable and sublime expression, as well as the subtle modeling of forms and atmospheric illusion that Leonardo painted. We wonder, we delight in his work, and while we may take note of the material that Leonardo used, we don't offer accolades and praise to the oil paint and the poplar panel on which it was painted, but this is merely the medium of Leonardo's art. Now, while his painting is an object of wonder, the real source of wonder is the artist himself. In other words, a masterful painting points beyond itself to the genius of the artist, and that's the pointer that is exactly our point in our discussion of pointers in the small and in the large. Just as the Mona Lisa points to Leonardo da Vinci as the actual creator, so does the created order, I believe, point to and speak of its artist. So I want to take a short walk through the universe in both its tininess as well as its immensity, and stop off here and there to note some of these pointers. Now, first, in order to prepare us for our journey together, I want to talk a moment about scale. We're going to be moving through enormously small and large distances measured in meters, and the notations we're going to be used are called powers of 10, which is really just a shorthand way of writing a long number. For example, 10 to the 6th power simply denotes a 1 with 6 zeros, otherwise known as 1,000,000. So the number of the power represents the number of zeros that are tagged on to number 1. So that's also called scientific notation. Now let's look at this concept in physical terms. An oak tree is about 10 meters high, so it's represented by 10 to the 1st power. Whereas a young boy is only about 1 meter high, so his height is represented by 10 to the 0 power. And a rabbit is about 1/10 of a meter high, or 10 to the -1 power. So as you can see, each of these steps represents a 10-fold jump in size, and we're going to be making these 10-fold jumps in size throughout our journey to the very small and then up to the very great. So I want to begin then by zooming down. And I want to zoom down into the microcosm, and I think we're going to find some areas where people are not fully familiar, and I'm hoping to kind of stretch your minds and your imaginations on the mysteries that are in the microcosmic world. Now, to launch the first half of our journey, I want to start with our friend Steve, who's napping in a Chicago park on a warm October day. And our field of view, as we're looking out of a square window, is 10 to the 0, which is 1 meter across. Now, as we zoom into Steve's hand, we've jumped 10-fold down to 1/10 of a meter. So let's take a look at a few of the objects that we see on this scale. At 10 to the -1 meter, we see beauty and we see order and small detail. We find small creatures with fascinating features like this juvenile owl. We find artful creatures like the chameleon with a sticky tongue about as long as his body, but with deadly accurate aim. We find larger insects such as this giant woodlouse crawling on this girl's hand. And we find some very odd-looking creatures such as the rosy-lipped batfish. And no, his lips are not photoshopped. That's his real mouth. And yes, his elongated fins that he uses to walk on the seafloor are real. Things I could never even dream of or imagine in the created order. We find on this order of magnitude spectacularly painted plants like these from Norway. We see alien or even diabolical-looking insects such as these different species of praying mantis. Now I want to take another another move down to the thumbnail sketch, another tenfold jump deeper down to 10 to the minus 2. And here we begin to see the creases of skin on Steve's hand. And these creases are designed, by the way, to give the skin its flexibility. Now at 10 to the minus 2, we see smaller creatures like this Atticus moth, which smells through its large antennae. And we also find the colorfully bizarre wattle cup caterpillar, whose prickly body will liquefy and then metamorphose into a beautiful Australian butterfly. In the seas of Indonesia, just in the last several years, scientists have discovered a new species called the pygmy seahorse. Its body wonderfully mimics the pink polka dot textures of the coral which it inhabits. At this scale, we also see some of the nearly 400,000 beetle species like these two. Now, asked what could be inferred about the mind of the Creator from a study of his works, the British scientist J.B.S. Haldane dryly replied, "An inordinate fondness for beetles." Because we have no idea why we need this many beetles. But this apparent fondness has resulted in beetles of a magnificent range of shapes and colors and patterns and sizes. Beetles that in fact are beautiful enough to collectively become artwork themselves, as are butterflies and dragonflies. Now, as we move deeper to 10 to the minus 3, we now approach the edge of human vision. And at this scale, we can behold one of the many marvelous shapes of a simple snowflake, all of which are said to be as individually unique as human fingerprints. At the farthest edge of this scale, we find curious creatures, such as this hairy human flea, or this peculiar maggot of the bluebottle fly, which looks like he has buck teeth. And amongst the roughly 400,000 known species of plants, we see the beauty and ingenious shapes of various beautiful pollens on the scale of magnitude, such as these fine colorized pollen accents which are nestled in a purple forget-me-not flower. Now we move under the microscope, and we've moved beyond the limits of human vision at 10 to the minus 4 meters into the world of the microorganisms. And 10 to the minus 4 meters represents the width of a human hair. Now here we find, on this scale, the living organisms that make up what we call pond scum, diatoms. They're actually extremely beautiful, with two tightly fitting glass-like halves, which often have spines and ribs radiating out from them. Oil droplets inside the skeleton help to keep the diatoms afloat in the surface waters, where the sunlight can blaze through their transparent casings to the golden brown photosynthesizing pigments within. Now, these freshwater and marine diatoms bear resemblance to some of the most famous architectural designs made at a much larger scale, like the Sydney Opera House, or like this one that looks obviously like the Leaning Tower of Pisa. And 25 million of these can fit into a single teaspoon. So it's extraordinary the scale that we're dealing with here. Another kind of creature on this scale are radiolaria, which are gorgeous, minute marine creatures and important members of the zooplankton, especially in tropical seas. And these pieces of exquisite lacework are actually the translucent silica skeletal frameworks of some forms. And here's a close-up of the intricate radiolaria design. It's actually exquisite in its geometry, as you can see. Now, scanning electron microscopes, or SEM, have also produced these colorized images of a filter-feeding colonial marine invertebrate called a bryozoan. He looks like a happy or excitable little fellow. Now, as we delve deeper into Steve's skin, moving down to 10 to the minus 5 meters, we pass through a tiny blood vessel and we find within his blood a lymphocyte, or a white blood cell, which plays an important role in the body's immune system, as these specialized cells identify and destroy invaders. Now, our body has 50 million white blood cells standing on guard against invasion by foreign particles, plus a backup force 100 million times as large in the bone marrow should the need arise, and it activates them very quickly indeed. Here at 10 to the minus 5, we can see the fibrin mesh nets that hold back the blood in a blood clot. Now, this remarkable system is programmed to clot our blood so that we don't bleed to death, but it's also programmed to know when to stop the blood clotting so that it doesn't continue to clot all the rest of our blood. It's a very delicate cascading balance. This scale can also be represented by the thinnest skin in the human body, the eyelid, which is 5 times 10 to the minus 5 meters thick. Now, at 10 to the minus 6, going down another order of magnitude, we have moved now inside the roughly lymphocyte, only to face another surface, a protective membrane within the cell that encloses its nucleus. Now, the minute pores open and close to allow beneficial substances to come in and out, and to keep detrimental substances out of the nucleus. Now, at this scale, we encounter a tiny life form, a bacterium called E. coli, which is found both in human intestines and in fecal material. And these tiny organisms are the reason why swimming pools are evacuated when small children accidentally defecate while in the pool. Now, E. coli can be quite harmful to other humans. But one interesting feature of this bacterium is its whip-like tails called flagella. And these act like the propeller of an outboard motor. Very sophisticated indeed, because a micromolecular acid power motor propels the flagellum to move the bacteria around. Now, when microbiologists first discovered these self-replicating micro-machines, they were amazed to see that they were designed in exactly the same fashion as everyday electric motors that humans design on a much larger scale. For ceiling fans, for example, complete with a rotor, a stator, a drive shaft, and various bushings. Some have called these molecular motors the most efficient motors in the universe, far more efficient than anything we could ever craft, and far more sophisticated indeed. In fact, many of them are engineered with similar designs as their human counterparts, and over 100 of these molecular motors are now known to exist inside the cell, with very specific analogies then to these human-designed motors. It's remarkable things going on in this order of magnitude. 10 to the minus 6 also represents another important milestone. It's the threshold of life. Nothing below this scale is alive. It's inanimate matter. Thus, when we go one more step downwards, we reach the DNA, which is not alive. We're now below the threshold of life. And we move within Steve's hand and his white blood cell's nucleus, and we find a tightly coiled mass of enormously long molecules of deoxyribonucleic acid, or DNA. And these utterly amazing molecules store the information, or the recipe, if you will, to build a complete human being with all its unique traits. DNA is a molecular blueprint, or a molecular library. Every cell of every living thing contains a unique version of its DNA instruction set. Your body has approximately 75 to 100 trillion cells. Each of these cells has approximately 6 feet of DNA, tightly coiled in the nucleus. That's an awful lot of DNA. It would reach to the sun and back in your body about 400 times. So it's extremely rich in its complexity and variety. This image, by the way, shows the X-shaped, tightly wound chromosome, strands of DNA, which are inside the cell nucleus. And then when these chromosomes are unwound, they reveal a 6-foot-long strand of DNA in its double helix structure, which consists of 4 paired chemical bases labeled C, G, T, and A, which are called nucleotide pairs. And these 4-letter chemical alphabet, really this spells out the instruction set that's required for generating proteins. The sequence of information and contained in the entire strand of DNA is what is referred to as the human genome. Now at 10 to the minus 8, we get a better picture, a close-up of the physical structure of the DNA, and we have the famous double helix. On this ladder-like structure is contained 3.2 billion nucleotide pairs of information, which are encoded to make proteins for body parts such as a heart, hand, or hair. And we're not talking about just a little bit of information contained in DNA. We're talking about a non-living substance which is encoded with the most densely packed, the most elaborately detailed assembly of information in the known universe. This is actually highly coded information. And to give you a physical analogy to picture the massive amount of information stored in the DNA of each of your trillions of cells, consider this, that DNA is estimated to contain instructions that, if written out, would fill 1,600-page books. DNA provides each cell's sealed chemical credential of membership in the body, all in the area 10,000 times smaller than a pinhead. Now, to read a person's genome sequence out loud without stopping at a rate of 10 bases per second, A, T, C, G, A, T, C, G, A, T, and so on, would take 9.5 years at that rate to finish. Or at a more realistic pace of 3 bases per second rather than 10 per second, and a 40-hour reading week rather than non-stop 24 hours a day, would take 132 years just to say it all out loud. DNA contains an enormous amount of rich coded information. Now at 10 to the minus 9, we zoom in even closer to the individual DNA molecules, and at this scale we find also what are called carbon nanotubes, which are cylindrical arrangements of carbon atoms of incredible strength that have been manipulated. And they can be grown for use in nanotechnology, in electronics, in optics, and in other fields of material science. We also find on this scale crystal structures of beta-catenin, which medical scientists are studying as key components involved in the regeneration of organs and fins of the zebrafish. Knowing how the zebrafish regenerates its body parts is hoped to have application for human organ regeneration. Going 10 times closer in, we are now looking at the outward or outer electron cloud of a carbon atom in the DNA. We're not merely looking at individual electrons, we're seeing really a representation of a cloud of negative charge associated with the carbon's 4 outer electrons. And at this scale, we find a basic water molecule, which is 2.8 times 10 to the 10 to the minus 10 meters in size. Now, speaking, by the way, of the outer electron cloud in the atom, there was a time when scientists doubted their existence, but others such as Ernest Rutherford clearly envisioned them. Not exist, why I can see the little buggers as plain as I can see that spoon in front of me, said Ernest Rutherford to Arthur Eddington when the latter was musing aloud at the table as to whether he would ever come to know electrons as more than mental concepts. The image that we see here now is 10 times closer in, And now it represents the cloud of charge of the two inner electrons. We've looked at the four outer, now we're further inside, and we're looking at the two inner electrons of the carbon atom. And as in the previous picture, individual electrons cannot be resolved. Essentially, what we're seeing here is a display of the probability of finding an electron in this field of charge. It's not like an atom is some hard object, something that we can touch like that, but it's much more subtle than that. Now, at 10 to the minus 11th power, we see the wavelength of X-rays. I think this kid's looking up at his father because the girl just called him a bonehead. But at any rate, we're looking at nuclear volume here, and when we go 10 times further in, for the first time, we're now beginning to see the nucleus. It's almost all empty space. The nucleus is a tiny, tiny component of each atom in your body. It's almost all empty space. And at 10 to the minus 12 meters on this scale, we're now within the electron cloud, and the small dot in the center of the image represents the nucleus of this carbon atom in the distance. And this scale also represents the gamma wavelength, which has been measured to be 1 times 10 to the minus 12 meters in size, or 1 picometer. Now, gamma rays are high-frequency electromagnetic radiation produced by subatomic particle reactions. Now we move even further in, 10 times closer, and we now see its nucleus containing a tightly bound group of 6 protons and 6 neutrons, thus called carbon-12. And to give you a feel for how relatively small 10 to the 13th or 1/10 picometers actually is, consider that the brown circle represents the diameter of a human hair, and you can see how comparatively small the scale that we're looking at really is. Or we take another tenfold leap, and we move closer now to the constantly dancing structure of a tightly bound carbon-12 nucleus. What is it that holds this nucleus together? After all, there are 6 protons, each carrying a +1 electric charge, crammed together with 6 neutrons in an incredibly tiny space. The mutual electromagnetic repulsion of the 6 protons is actually overcome by what physicists have dubbed the strong force, the strong nuclear force. Now, we have no idea of what it really is, but that's the label we place on the concept. We're clueless, but it's what holds atoms together. And the strong force, though, of the nuclei of the atoms, merely in 1 teaspoon of water, would contain enough energy to move the Queen Elizabeth II from New York to Liverpool and back. And that's just the strong force in 1 teaspoon of water. Now, this high-tech observatory, called the Super Kamiokande Neutrino Observatory, was designed to search for proton decay, to study solar and atmospheric neutrinos, and to keep watch for supernovas in the Milky Way galaxy. It represents the extreme level of technological sophistication required to study particles on this scale. Going 10 times closer in, the image on this page is an artist's abstract rendering of the, quote, surface of a proton. It's a kind of boundary layer of 3 strongly interacting quarks that make up the proton. To illustrate the atom and its subcomponents, here's a representation of the atom with its orbiting electrons and nucleus, and the protons and neutrons which make up that nucleus, which themselves are made up of 3 subparticles called quarks. And there are 2 up quarks and 1 down quark for every proton. Now, as we move deeper, we're now outside the 2 up or the 1 down quarks, and everything at this level is and behaves in an unfamiliar manner to us. As we approach the quark 10 times further in, now we're at 10 to the minus 17 meters. Normal rules of physics no longer apply. This becomes an unpredictable world, moving more deeply into the philosophical as we acknowledge, for example, that all we touch is merely compressed energy, whatever that is. We have the up and down quarks. At this scale, we're moving actually within one of the two up quarks, or within one of the single down quarks that make up the proton. Now I'm going to jump 3 orders of magnitude further in, now down to 10 to the minus 21. And with this quantum leap, we reach the realm of what are called preons, which are point-like particles that are conceived to be the building blocks of quarks and leptons. And then jumping another 3 orders of magnitude, another quantum jump, now I'm down to 10 to the minus 24 meters, we reach the scale of the elusive neutrino, a particle that passes through matter undisturbed almost at the speed of light. Now I'm going to take a huge leap down to the lowest theoretical level, 10 to the minus 35 meters, which brings us to the smallest theoretical boundary of length, which is called the Planck length. And this is a realm of great conjecture and speculation involving string and M theories, and of trying to find a grand unifying theory or a theory of everything. It's as philosophical as it is scientific. Now that we've moved into this realm that's not exactly familiar to you, let's retrace our steps through Steve's atoms back outside his hand. So again, we go to the innermost limits of the subatomic world, and now we've zoomed out to the scale of the neutrino, and then to the preons, which make up the quarks, to the up and down quarks. Now we're outside the quarks, further outside the quarks. Now we're outside the surface of the proton, and now we're outside the proton and neutron cluster that represents the carbon-12 nucleus. Another jump up tenfold, and we reach the carbon nucleus, the atomic nucleus, another tenfold leap, and now around the inner electron cloud, and now at the atomic surface of the carbon's outer electron cloud, out to the DNA molecule, to the double helix of the DNA, to the strands of DNA inside the cell nucleus, outside the nucleus of Steve's white blood cell, to the white blood cell as a whole, to the skin surface visible only with a microscope, to the edge of human vision, to the creases of the skin, to the hand, and back out to Steve napping. So now that we've journeyed to the innermost limits of knowledge, what I want us to do now is to zoom up in the other direction. And I want us to look at the outermost limits of human knowledge and see what we can find along the way. So we now move from the microcosm to the macrocosm. Now, we're back to Steve, and at this scale, our window or field of view is once again sized to 10 to the 0 or 1 meter. And on this scale, organisms and objects we see at this level are, of course, completely familiar to us, like this beautiful assortment of multicolored tulips, or this tulip field in Holland, or the iridescent blue-green brilliance of a male peacock's plumage displayed during courtship, or the hideous display of aggression of Ethiopian Galata monkeys. Now, as our field of view takes a tenfold jump in size to 10 to the first power, we see our friend Steve and now his wife Nicole, and she's reading a magazine there at the bottom, on their picnic blanket. Now, this picnic will be the center of every picture outward to our view among the galaxies. At the scale of 10 to the 1 meters, all is common to us, but even the common can be both beautiful and fascinating. On this scale, we also find magnificent geothermal geysers like this one in Nevada, whose minerals, algae, and cyanobacteria give it its resplendent color. In the sea, we also find bullet-shaped ferocious eating machines much larger than us. Or we find freakish creatures such as this goblin shark, which is one of many creatures previously known only by its fossilized remains until this living fossil was recently discovered in its unchanged form. Or this oarfish, whose bizarre body plan may have provided material for sea dragon lore. And from the fossil record, we find the largest living land creature, the 120-foot long Argentinosaurus, which paleontologists estimate weighed over 100 tons, which is about the weight of 7 city buses. Paleontologists also estimate that 95% or more of all species that have ever lived, including the Argentinosaurus, are now extinct. Now at 10 to the 2 meters, that is 100 meters, we see more of Steve and Nicole's world. We now see cars, the highway, and boats in the marina. On this scale, we see trees. Giant trees are the largest of all individual living forms. And in the chain of species, trees are a pinnacle, a perfect living sculpture. Trees defy gravity. They're the only natural element in perpetual movement toward the sky. They grow unhurriedly toward the sun that nourishes their foliage, and they have the power to capture light's energy. They store it and feed off it, turning it into wood and leaves, which then decompose into a mixture of water, mineral, vegetable, and living matter. And so gradually soils are formed. At 100 meters, we have a unique view of such natural phenomena as the Grand Prismatic Spring at Yellowstone National Park, which is the largest hot spring in America. Now, the vivid colors in the spring are the result of pigmented bacteria in the microbial mats that grow around the edges of the mineral-rich water. We also find on this scale the Perito Moreno Glacier in Chile, the world's largest glacier, towering 240 feet above Argentine Lake. Jumping up another order of magnitude, we see larger structures. We see now Lakeshore Drive, Soldiers Field there in Chicago. We see an airstrip, boat docks, museums. And this is the last power of 10 at which individual living things are identifiable. The largest animal and single plant that have ever existed now fit within the central square. However, we have many man-made structures on this scale, such as the Golden Gate Bridge in San Francisco, which is 8,891 feet long. And on the scale, plains areas in the United States occasionally see storm formations, like this supercell thunderstorm. And these supercells breed tornadoes with winds exceeding 200 miles per hour. At this scale, we can also see both man-made and natural patterns emerging from the surface of the earth, such as this farmland in Ecuador, or this intriguing natural heart shape in Vaud, New Caledonia, which is a French territory. Now we zoom out another tenfold and we begin to see the city of Chicago, home to millions of people, and this whole structure is still basically familiar to us: city districts, parks, harbor, and lake. But 10 to the 4th meters represents yet another threshold. All known life on Earth exists within a thin layer stretching from the ocean depths in the Mariana Trench, located in the Pacific, to a point about 6 miles above the Earth's surface at Mount Everest. And this layer, this thin layer known as the biosphere, measures 12 miles and is comparatively no thicker than the print on a billiard ball relative to the diameter of the Earth. That's where all of life is. And there's no life beyond this narrow threshold. I think that there is increasing evidence that our world may be the only absolute exception in the cosmos, that life may only exist within the exceeding narrow band of this biosphere. Therefore, 10 to the 4th represents the threshold of life. No life exists above it. Only inanimate matter exists beyond it. Now, as we zoom out again, we see Metro Chicago and Lake Michigan. Flying in an airplane, we would be barely visible on this scale to Steve and Nicole looking up from us from their picnic, still at the center of the yellow rectangle. Going out now to 10 to the 5th, which is 62 miles, we can see a spectacular view of the Earth and the space shuttle, and of Alaskan snow-capped volcanoes, and of hurricanes, such as this one, Hurricane Emily, spinning off the coast of Mexico. Now take another tenfold leap, and now we can behold Illinois, Wisconsin, Indiana, Michigan, and the whole of Lake Michigan. At this point, the work of human hands is no longer visible, at least during daylight. At this distance, in the upper atmosphere of the Earth, luminous phenomena called auroras occur. Now, auroras are caused by the interaction of energetic particles, electrons and protons, from outside the atmosphere with atoms of the upper atmosphere. And auroras occur primarily at high latitudes like this one in Norway, but during periods of intense solar activity, auroras occasionally extend to the middle latitudes, such as this one gracing the skies of Oklahoma. Now, this distance also provides the last glimpse of the work of human hands, visible only by the light at night. At this distance, we also begin to see the curvature of the Earth. Going 10 times further out, we now reach 10 to the 7th meters. We move now from an essentially flat image to a picture that gives us a sense of depth. North and South America are now visible, and though map makers had for centuries prepared us for this sight, it did not become a reality until 1967. The diameter of the Earth is 7,926 miles, and despite its massive size, the constant movement of the Earth is imperceptibly smooth, even while spinning 1,000 miles an hour, while simultaneously orbiting the Sun at 66,000 miles per hour. In addition to these orbital speeds, our Milky Way galaxy itself is also imperceptibly moving our planet through space at a very high rate of speed. In other words, we're constantly in motion within the cosmos. Moving one more scale outwards to 10 to the 8th meters, here now we see the whole Earth isolated, elegant, and fragile. Our picnickers are still in the middle of this orange square. And then we go out and see at 10 to the 9th meters, the furthest place our own kind has yet visited, the companion moon, our nearest celestial neighbor, whose orbit is represented by the gray line. Bright moonlight and the tides witness the moon's proximity, and yet she could be wrapped neatly in a cloth smaller than the size of 2 North Americas, with a diameter about 1/4 that of the Earth, but it's still uniquely large compared to its host planet. In visiting the farthest place humans have ever traveled, Apollo 17 astronaut Buzz Aldrin described the environment of the moon as a magnificent desolation. With no water, no atmosphere, no food, the moon is an inhospitable place for our kind, and life is only possible there using portable life support systems. Now here's an image of the far side of the moon, which had never been seen before the Apollo 16 mission. And surprisingly, the rough and battered surface of the far side looks very different from that on the near side. The near side is covered more with dark, smooth lunar maria, which are large basaltic plains formed by ancient volcanic eruptions. Now, the green band in this image that we see at 10 to the 10th meters represents 4 days of Earth's orbit around the Sun, while the faint white oval there represents the Moon's orbit. Now, if you lived on the Moon, you could watch not only sunsets, but also beautiful Earth sets. Only in 1977 did we first see an image like the one you're seeing, a fully Copernican perspective in this photograph of both our Earth and its companion moon from outer space. Here we have the Hubble Space Telescope, which is one of the key instruments that have expanded our knowledge of astronomy in the last 20 years, more than the sum of all astronomical knowledge since the beginning of time. We live in an exciting time of discovery. And moving further out, we see a portion of the inner solar system. looking at the inner planets. The three colored bands that you see represent the orbits of three of the four inner planets, Venus, Earth, and Mars, all of which have rocky crusts and metallic cores. Now here's a relative size comparison of the inner and outer planets to the Sun and to each other. Now Earth, of course, the third planet from the Sun, with Venus being the second, and note that Pluto, which appears as a mere dot in this image, is smaller than the United States, and it's been now reclassified as a dwarf planet. No longer makes the qualification of a full planet. At 10 to the 11th meters, we see Mars as the fourth planet from the Sun, and here are some of the latest images from the recent Mars Explorer rover mission. And these images are the first of their particular kind for planet Mars. More Martian surface, appearing with intriguing gray and black paintbrush-like strokes of unknown composition. And while in this image the brown projections may look like trees on Mars, they're not. These clusters of dark brown streaks were photographed by the Mars Reconnaissance Orbiter in 2008 on melting pinkish sand dunes covered with light frost. Now zooming out 10 to the 12th meters, we now see the orbit of the inner planets surrounded by the orbit of Jupiter. And here is Jupiter, the largest planet in our solar system. Its diameter is roughly 1/10 that of the Sun, but 10 times that of our Earth. Now here's a color-enhanced close-up of Jupiter's giant red spot. The eye is a violent hurricane moving counterclockwise at over 300 miles per hour. And it's been raging now for centuries. And it's almost 3 Earth diameters across, to give you a sense of the scale of this giant storm. In jumping for a moment back to the Earth's vantage point, in this image taken in Turkey, Jupiter is the brightest light in this photograph of the Mediterranean sky to the left of a band of the Milky Way. At this distance, we can see from the outside in, at 10 to the 13th meters, the orbits of Pluto, Neptune, Uranus, Saturn, Jupiter, and the 4 inner planets clustered near the image in the center. And here's a NASA image of Saturn's rings, falsely colored to represent the different bands. And another recent NASA image of Saturn. Indeed, 755 Earths could fit inside Saturn's volume. But Saturn is so light that if there were an ocean large enough, Saturn would actually float on it. Its specific gravity is less than 1. 10 to the 14th meters, we're now at the magnitude where we see the solar system almost entirely within the inner square. The planets, as they move around the Sun on nested ellipses, are mapped by colored lines. Note that in this image, the star background is unchanged and will be unchanged in the next several orders of magnitude because of the incredible distance of the stars in our Milky Way galaxy. A great cloud of icy comets orbits slowly here, though invisible in the weak sunlight. And we see comets only as a few of them move each year into the brighter regions near Earth. And there we catch sight of them moving in the sky like temporary planets, the solar wind ionizing their long tails. Comets are made of frozen gas, carbon dioxide, methane, and ammonia, and dust. And they can be significantly larger than Earth. This is Comet Lulin, which passed near Earth in February of 2009. Comets are known largely for their tails, and in the case of Comet Kohoutek in 1973, its tail stretched 200 million miles, which is considerably farther than the distance from the Earth to the Sun, and the longest recorded comet tail measured 360 million miles. At this distance, the Sun is the brightest object, set against a background of fainter stars beyond. Now, returning to Earth just for a moment, this time exposure image captures the rotation of the Earth and the beauty of the stars overhead. As late as the 18th century, astronomers had a simplistic view of the number of stars, trying to bring order to them by connecting them into fanciful figures of men, animals, and other mythical creatures. But today we know that stars are exceedingly more numerous and more complex than the astronomers of the past could ever have imagined. Moving out tenfold really doesn't change our view of the sun. We're now at 10 to the 16th meters. Again, it's a 1 with 16 zeros after it. Now our sun is remarkable. The star, which is a type G yellow dwarf, is the origin of virtually all the energy that sustains life on Earth. Even the simplest earthly life forms, such as diatoms and phytoplankton, have a relationship with this star located 93 million miles away, being marvelously able to transform its light energy into chemical energy. This massive thermonuclear reactor is the source of all of our weather and the arbiter of our climate, and it produces a remarkably stable energy output that varies by no more than 0.1% over a decade. This is important because if these qualities were not there, if the sun were not precisely as it is, there could be no life on this planet. 1 million Earths would fit inside the sun. Now, the fastest humans have traveled on the surface of the Earth is a little under 800 miles per hour. The fastest military aircraft, such as the SR-71, can travel through the air at about 2,200 miles per hour. But these speeds pale in comparison to the speed of light, which travels at 186,000 miles per second, or 700 million miles per hour. So when we talk about a light year, we're talking about the distance light can travel in 1 year, which is about 6.9 trillion miles. Like the powers of 10 notation, a light year is a short way to describe enormously large distances. So, for example, it would take sunlight reflected off the moon, which is 252,000 miles away from Earth, 1.2 seconds to reach us. Now, since our sun is 93 million miles away from Earth, sunlight requires about 8.3 minutes to travel to our planet. Now we're at minutes. Then we go up another order, where Pluto is so far away from the sun that at 4.6 billion miles, it takes sunlight 5 hours and 45 minutes to reach it. It gives you a perspective. So that really you could say the diameter of our solar system is a little under 12 light hours. Now, if an intense light were shined from Pluto to the nearest star, known as Proxima Centauri, which is 29 trillion miles from Pluto, it would take about 4.3 years to reach. Now, our Milky Way is so massive that at 69 quadrillion miles in diameter, it would take light 100,000 years for it to cross from one edge to the other. To give you a feel for the size of our Milky Way galaxy, if you could consider going back to our, let's make it and exaggerate a little bit, make it 12 light hours in diameter, our solar system, and if you reduce that 12 light hours to the size of a coffee cup, how big would our galaxy be on that scale? And the answer would be larger than North America. It's incomprehensibly large. Now, the relative size of our sun is interesting for us to consider, because as a yellow dwarf, 93 million miles away from Earth, as we said before, you have this imagery here of how big is our sun really, and if we looked at it, we see that it's relatively modest in size. Large, of course, compared to Jupiter, but really, compared to the star Sirius, rather modest, our sun, in size. But Sirius is really itself much smaller than the star Pollux, which is much smaller than Arcturus. And Arcturus, in turn, is tiny compared to Rigel, which is small in comparison to Aldebaran, small in comparison to Betelgeuse, and small in comparison to Antares. Our sun would be barely represented by a pixel in this comparison. But Antares isn't the largest known star, nor is S Doradus, or even KY Cygni, but rather VV Cephi. Hence, a sun worshipper can find far more worthy objects than ours to worship. Now, I want to multiply our scale by 10. We've moved out into the vast, mostly empty star system and the star realm. At 10 light years in diameter, stars located within that range constitute this cluster and this cluster. And again, if we could travel at the speed of light, we could reach these relatively near stars in about 10 years, but note the little red star labeled Proxima, which is near our sun. Now, Proxima Centauri is the closest star to our sun, being only 4.22 light years away, and here it is at the center of a star field in the background. Astronomers estimate that there are about 200 billion stars or so in our galaxy, and that there are about 200 billion galaxies. Some estimates range as much as 1 trillion galaxies. And thus there are more stars in the visible universe than there are grains of sand in all the deserts and in all the beaches of the earth, possibly by a scale of 10 times more. Inconceivably large as well. They're not close to each other. They're inconceivably distant from one from another. In fact, on this scale, all the stars from all the previous views lie within our orange square, and we're now about 100 light years from the Earth. And here, on this scale, we see the Pleiades star cluster, which is called the Seven Sisters, seen in infrared light. At this distance, we also behold the planetary nebula, which is entitled the Helix Nebula. This orange gas cloud was emitted from a dying star located in the center of that eye. On this scale, we are within an arm of our disk-shaped Milky Way galaxy. So at 10 to the 19th meters, we can begin to see the shape for the first time of the spiral arm that we're on in our Milky Way galaxy, right amongst a host of stars visible here as individuals. And at this level, then, 1,000 light years, we witness more nebulae, which are illuminated clouds of dust and gas emitting from a star. In this case, the famous Horsehead Nebula, and the well-known Orion Nebula, which is located right in Orion's belt at a distance of 1,500 light years. Here's the braided serpentine filaments of glowing gas from the Medusa Nebula, and the Flame Nebula, the Eskimo Nebula, as imaged by the Hubble Space Telescope in the year 2000. The Cat's Eye Nebula, 3,000 light years distant. The Butterfly Nebula. The lovely Blue Lagoon Nebula, 5,000 light years distant. The Rosette Nebula. The Eagle Nebula. The Heart and Soul Nebulae. The Crab Nebula, 6,500 light years away, and the intriguing W5 star formation region. Also the Jellyfish Nebula at the lower right of the image. And we go beyond this scale 10 times further out, and now we reach 10 to the 20th meters. And we've traveled now outside the flat disk of our galaxy, and we're looking back at a portion of the spiral arms. Now, on this scale, there are supernovae, which is an exploding star, except these stellar explosions are 100 million times brighter than the sun. This is a composite image of the Cassiopeia A supernova remnant. While this supernova, Eta Carinae, is located only about 7,500 light years away, it gives a clear picture of a stellar explosion. And now, jumping 10 times further out, we see a garden of galaxies. We move in that direction. We look face down on the whole of the Milky Way spiral. 200 billion stars, mutually bound by gravity, encircle the central region. External galaxies akin to our own are scattered throughout space as far as we can see, and they too slowly rotate as they drift. Jumping back to Earth for another moment, let's take a look at the Milky Way. When it doesn't have to compete with light spillover from cities, a significant portion of our Milky Way galaxy is visible from Earth, as in this image taken in Wyoming, or this image of the Milky Way galaxy from the Badlands of South Dakota, or in Australia. Now here's an artist's depiction of our Milky Way galaxy. We're located here in the Orion Arm. So you are here. And at this scale, we'd need an electron microscope in order to see our Earth. It's incomprehensibly large. And the Milky Way itself is surrounded by several dwarf galaxies, typically containing a few tens of millions of stars, which is insignificant compared with the number of stars in the Milky Way itself. And this map shows the nearest dwarf galaxies. They're all gravitationally bound to our Milky Way, and they require billions of years to orbit it. Note the position of the Large Magellanic Cloud. And here's a NASA close-up of a portion of that Large Magellanic Cloud with its famous seahorse shape, and another view of the Large Magellanic Cloud showing the Doradus Nebula, and yet another view of this neighbor galaxy, not our own, showing the Tarantula Nebula within it. Now we zoom out further yet, 10 times further out, 10 to the 22 meters, to the local group of galaxies, and this image shows the small and large clouds of Magellan. Again, irregular galaxies near our own spiral galaxy. But there are many galaxies in our local group of galaxies. Note especially the Andromeda and the Triangulum galaxies, which are highlighted in orange. Now, more specifically, the Andromeda galaxy is our nearest giant galactic neighbor at 2.5 million light years away. And like ours, it too is a spiral galaxy. Beautiful image. The second largest galaxy in our local group of galaxies, after the Andromeda galaxy, is called the Triangulum galaxy. We also have many other neighbors, such as the Fireworks galaxy with its beautiful pink and white pinwheel shape, or the Centaurus A galaxy, which contains a supermassive black hole. 10 times further out, we reach clusters of galaxies. Our galaxy at this scale is hardly visible. The dots are the galaxies of our own cosmic region, each single bright spot made by the summed light of stars by the billions. This galaxy map shows how galaxies tend to cluster into groups. You see, our galaxy turns out to be part of a cluster known as the Virgo cluster, which consists of a concentration of several hundred galaxies. So we're part of this larger, our local group is there, part of a larger Virgo cluster of galaxies. And this is, for example, the barred spiral galaxy, NGC 4731, which is part of that Virgo cluster of galaxies. Also, on that level is the striking Sombrero galaxy, the narrow profile Needle galaxy, the big, beautiful spiral galaxy NGC 1055, and two spiral galaxies that are actually in the process of collision. Now, these galaxies are so massive that they may pass through each other without their stars ever touching. But these two galaxies, however, have collided, triggering furious episodes of star formation near the center of the cosmic wreckage. Now we go out 10 times further. We are now at 10 to the 24th meters, and we now reach not clusters, but what are called superclusters of galaxies. Groups of neighboring superclusters of galaxies include these, as well as these. Note the Perseus supercluster and the Hercules superclusters. So you get a picture of what they look like. Because each of these fuzzy blobs is actually a galaxy, together making up the Perseus supercluster, which is one of the closest clusters of galaxies. So every dot you see is a galaxy, many of which have hundreds of billions of stars each. Again, incomprehensibly large. These superclusters of clusters, going to from the Perseus to the Hercules supercluster, we have an archipelago of island universes some 500 million light years away. Again, every object that you see is a galaxy. At 10 to the 25 meters, again a 1 with 25 zeros after it, what we discover is that most of space looks empty like this. The glow of distant galaxies like clouded dust. Now this emptiness is actually normal. Our own bright home world is the exception, and a tenfold larger view would show a greater void with a filamented structure. Now here at over 1 billion light years from Earth, the Hubble Space Telescope finds this massive, compact galaxy supercluster. And this, called the bullet supercluster of galaxies. Also, on this scale, quasars are the brightest objects in the universe, so bright that they can be seen from across the universe. Observations continue to show that most quasars are surrounded by a relatively faint nebulous patch. Astronomers are trying to identify the nature of these patches, and the image here that we see of a false color picture shows a central quasar which is embedded in an unusual elliptical galaxy. Now, this supercluster image reveals 5 quasars, the bright white spots. The others are galaxies. So we have hundreds of galaxies and 5 bright white spots that are quasars. Every pinpoint of light then, not stars, but galaxies. Reaching out to the outermost limit, we hit 10 to the 26 meters, about 10 billion light years. And we approach the outermost limits of the known universe. Now this map attempts to depict symbolically the entire visible universe. The galaxies in the universe tend to collect into vast sheets and superclusters of galaxies surrounding large voids, giving the universe a cellular kind of appearance. Now the furthest known galaxy is the Abell 1835 IR 1916 galaxy, which is located an estimated 13.2 billion light years away. NASA's Wilkinson Microwave Anisotropy Probe, also known as WMAP, has mapped the cosmic background radiation, which is the oldest radiation in the universe. And it produced the first really fine resolution full sky map of the microwave sky. And it shows that, like the planet Earth, the universe itself appears to be globe-like in structure, and the WMAP data reveals that the universe appears to be made up of roughly 5% ordinary atomic matter, about 23% dark matter, and 72% dark energy. Now, astrophysicists don't know what dark matter and dark energy are at all. But they like names and they like to label things to make them seem to know more than they do. What this tells us is this: approximately 5, possibly only 4% of all the material in the cosmos is not the stuff that we can see and touch and taste. It's mysterious energy and matter that we see that's called dark. Now, what we see here is the result that we're surrounded, really, in many ways, by mystery. We really know so little about our own planet, much less about our own solar system, our galaxy, our universe. Scratching the surface, we quite literally live in the midst of profound mystery. I want to take the journey back. Let's head back to planet Earth, returning to Steve and Nicole's picnic. You'll remember them. Mighty small on this scale. Here we are back at the outermost limits of our universe. And we drop down tenfold and witness galaxy superclusters and quasars. And zooming in, we find more galaxy superclusters. And then another, their subcomponents, galaxy clusters. And we begin now from this scale to see our own galaxy and 2 of its cosmic neighbors. And we zoom down above the Orion arm of our Milky Way galaxy, down into a spiral arm, and past breathtaking nebulae of all shapes and colors on this scale, moving between the stars, hundreds of millions upon hundreds of millions of stars, and more local stars, until finally we see our sun in the distance, moving still closer to our sun. And now on this scale we begin to see the orbits of the planets in our solar system, which we now see more closely. We move within the orbit of Jupiter, down into the inner planets, into the Earth's orbit, and then into the Moon's orbit, until we can finally see our planet in the distance, and now closer, moving down to the Great Lakes area, down into Illinois, down into Chicago, above Soldiers Field and the neighborhood of our picnickers, down to a grassy park, down to Steve and Nicole's picnic, and back down to Steve where we started. Now, the complete range of size scales between the largest and the smallest objects in the cosmos is indeed literally astronomical. The observable universe is 100 million billion times larger than a human, while humans are 1 million billion times larger than a proton in the nucleus of an atom, an enormous scale stretching the imagination. Now I have to ask the question, what does all this mean? It's always a good thing to say, what's this all about? Well, why have we taken this expansive journey, and what's the point? I want to return to where we began. Our main point is that the magnificence and expanse of nature, I believe, tangibly points to God's supreme greatness. For those who have the eyes to see and the ears to hear, my view is that the created order points beyond itself to truth. And that the natural points to the supranatural. That is, the creation points, I believe, beyond it to its creator, just as a painting points beyond itself to the artist. And we know this intuitively, and there is plenty of reason, I think, in nature to back up our intuition. You take any dimension of this creation, the size of it, its beauty, its design, its order, its elegance, its complexity. It's increasingly mind-stretching. Now, Romans chapter 1, verse 20 says as much. And in this text, Paul writes, "For since the creation of the world, His invisible attributes, His eternal power and divine nature have been clearly seen, being understood through what has been made." Which means that the visible creation testifies to and expresses God's invisible attributes. Nature speaks of God. Nature's design points to the grand designer. Nature is God's great pointer. Psalm 19 echoes this thought, saying that the heavens are telling of the glory of God and their expanse is declaring the work of his hands. Now we've seen that the universe is billions of light years in size, and that qualifies as an incomprehensible distance, and as such we are right to be in awe of his work. In fact, his creation is so filled with beauty and wonder that we must be careful not to worship his creation instead of him as his creator, as is so often done. That mistake has been made since the dawn of time and continues to this day. The creation's never about itself. It points beyond itself to the one who made it. Theologians call creation natural theology because nature reveals many aspects about our creator. This is why Oswald Chambers observed that nature to a saint is sacramental. To see a world in a grain of sand and to see eternity in a wild flower, to look and to see the glory of God in the smallest thing. Nature then, I think, is such that we, do well to make it a practice to look at every aspect of creation, large or small, and to meditate on what does it speak about its designer, its author. To practice his presence, I think, by noticing and meditating upon his artistry, including wonderful little creatures such as beetles, for which God seems to have, as we said, an inordinate fondness. Now, it's been said, by way of our third observation, that a little science estranges man from God. A lot of science, I think, can bring him back, quipped Francis Bacon, the English statesman, scientist, and lawyer. I think that believers have nothing to fear from the sciences and everything to gain, as honest science reveals the splendor, order, majesty, and mystery in the universe and continues to actually show it to be more elegant, more information-rich, more finely tuned than ever conceived before. And in this age of unprecedented skepticism, God, I think, has chosen to reveal unprecedented levels of information, complexity, and elegance to humanity, such as has never been seen until the last few decades. My fourth point is this, that if you've got a big God, you'll have little problems. Because he's big enough, I think, to take care of them, if he can manage this cosmos. However, if you've got a little God, you'll have big problems, because he's impotent. And when you consider the enormous expanse of the creation in every direction, it's safe to assume that God's far greater than that creation. He's boundless, and remember that when the inevitable trials of life come, he's more than capable of handling these things. It gives us perspective. And my whole point here in our time together is to stretch your mind, to stretch your imagination, to leverage the created order so that we see beyond those things to something far greater. Because the more we expand our imaginations and use the created order to do that on both scales, the microcosm and the macrocosm, the more we have a capacity then to actually worship and to see and appreciate the greatness of the mystery we call God. Now, the beauty and wonder of creation, for my fifth and final point, I think will pale in comparison to the beauty and wonder of the new creation. The natural realm demonstrates God's infinitely creative power, but it's fallen. And the New Testament teaches that this present earth, which is now marred by the corruption of the fall, will be destroyed and be rebuilt again by God. It also teaches that there'll be a new heavens as well as a new earth, a new order of physics, as it were. All of the creatures, all of the plant life, all of the beauty that we now enjoy in this present earth, I think are mere hints of the new and perfected heaven and earth that awaits us. So again, we can use this and leverage it in our minds and imaginations. So if this creation stretches our minds, or the beauty of the mountains, oceans, plains, or deserts please you, then you should really enjoy heaven, which will literally be beyond your wildest imagination because no mind has ever conceived it. It's beyond our cognitive equipment. What God has in store for those who follow him and in this life. We simply do not have the capacity to understand, much like a dog who lacks the cognitive capacity to understand the concept of reading a newspaper. And yes, you can teach the dog to fetch the paper, but try teaching him to read it. Now, from a dog's point of view, my imagination is he looks at his master and thinks he's being rather dull. Because after all, he could be chewing on it or playing with it. Why does he just stare at it? No category to grasp what's going on there. And in a similar way, I think that's an analogy. The boundless distance between us and God. We lack that capacity to understand what He has planned for us. But as this present creation hints, it will be full of wonder and beauty. Given the fabulous pointers we see in this creation, nature is God's pointer to Himself.
Thank you for listening to this talk by Dr. Ken Boa. To order additional talks on CD or MP3, or to learn about any of Dr. Boa's other Bible-based teachings, go to our web ministry at kenboa.org. That address again is kenboa.org. Or call toll-free 1-800-DRAW-NEAR. That's 1-800-372-9632.